All right, so I hope everybody is doing well. We're going to start today by reminding you where we kind of left off with last time. Last time we were looking at the idea of congruence classes modulo a subgroup. And we had this calculation in class showing that the congruence classes modulo a subgroup are essentially the set of all elements k times a, where a is an element of the group multiplied by all of the elements of the subgroup. So if you take a subgroup and you multiply all of the elements of that subgroup on the right by a, you produce something that's called the right coset of k. If you were to multiply on the left all the elements in the subgroup by a, then you would produce what's called the left coset. And our definition of a coset, therefore, is this definition that I have at the top. Let G be a group and let H be a subgroup of G. For any element in the group, if you multiply that element by the subgroup H, this is the set notation for that. Since you're multiplying on the left, this is called the left coset of H and G containing A, or the left coset of H and G induced by A. And then if you multiply on the right, it's called the right coset of H and G containing A. So I want us to get a little bit of a practice with it, and then we're going to talk about some of these bullet points. There is a question which is up on Learning Catalytics. So if you haven't logged in, there's the session ID. Go ahead and log in and look at that question and respond to it, and then that'll give us a place to start here this afternoon. It's good to see everybody. I'll give you about another 30 seconds or so. This shouldn't take very long. All right, almost everyone has responded. The correct answer is C. If you put B, it's likely you did the calculation in the wrong order. So let me explain. 1,3H, by definition of coset, is taking the set H and looking at left multiplication of all of the elements by the element 1,3. So this is kind of how I think of it notationally. So now it just comes down to, do you correctly calculate these permutations? Well, the first permutation here, 1, 3 with 1, we know that's just 1, 3. The second permutation, remember, you always read it from right to left. So it's 1 maps to 2, and 2 stays fixed. Then 2 maps to 1, but 1 goes to 3, so 2 goes to 3. And then you'll notice that 3 goes back to 1. So this is the correct coset. So the coset 1, 3H is equal to 1, 3, 1, 2, 3, which was answer choice C. So this is all a coset is in this course, is it's just left or right multiplication of every element in a subgroup by some element from the group at large. So this element 1, 3, 1, 3 comes from G. It's an element of the group that contains the subgroup, and I multiplied every element in the subgroup by that element. This element is called the representative of the coset 1, 3H. We'd love to think of it as a generator, but it's not quite like a generator is for cyclic groups, so we use the term representative instead. So 1, 3 is the representative. Notice that the representative itself is in the subgroup, or is in the coset. So the representative is in the coset. So I have a question, will that always occur? So question, in AH, is A an element of AH always? What do y'all think?
I think yes, since the identity has to be in H.
Why does the identity have to be in H?
Because it's a subgroup of G.
Because it's a subgroup. So since H is a subgroup, I don't know what the elements of H are, but I know the identity has to be one of them. So there's probably a bunch of other elements in H. The identity has to be one of them. So when you form AH, you will always have AE, which we know is just going to be A. So the representative of a coset will always be in the coset for which it's representing. That's one of the questions that we typically ask of cosets. There are many questions that we typically ask of cosets and many properties, important properties that they have in this course. So let me kind of give you a rundown of those. So the element A is called the coset representative of AH or HA. The process by which we're creating these cosets should remind you a lot of the mapping T sub A that that basically permuted the rows of the Cayley table from the last lecture. They're related, although they aren't the same. And we're going to talk about the relationship between them at a later lesson. Our concept of order is the same. So if I want to talk about the order of the cosets, we use the same notation. And it simply just refers to the number of elements that are in the set designated by each of these. So a couple of the questions that we want to tackle today, the biggest thing that we want to tackle today is, and we're going to do several more examples of this, what are the cosets for a given representative? And then for a given group, what are all the cosets up to equivalents for that group? Because remember, a coset is synonymous with a conjugacy class or a congruence class modulo the subgroup. So cosets are really about congruence classes or equivalence relations that are being passed onto a group. So some of the questions that we want to tackle is it possible to have two cosets that are equal even though their representatives are different? The answer is definitely yes to that, and we're going to show that that occurs. When do cosets not overlap? So this says that there's no element of AH that belongs to BH. So when do cosets not overlap? When are they mutually distinct or disjoint? We'll talk about conditions for that. We're going to talk about, does a coset of a subgroup have to be a subgroup itself? Let's tackle that question right away with this example that we just did. H is a subgroup, so H is a subgroup of S3, but is the coset a subgroup of S3? No, because it doesn't contain
the identity, right?
Doesn't contain the identity. It also doesn't contain the inverse of 1, 2, 3. The inverse of 1, 2, 3 is 1, 3, 2. So this thing is not a subgroup. In fact, because it doesn't contain the identity, you can start to think, what is the only way that you're ever going to have the potential for a coset to be a subgroup?
You would have to either multiply it on the left by the identity or by the inverse of one of the elements, right?
That's correct. So the only way a subgroup, the only way a coset would be a subgroup is if AH is equal to EH, where E is the identity of G. And I'm going to do a caveat. I'm going to say potentially for right now. We're going to dive into this a little bit more here in just a second. But the only way a coset would potentially be a subgroup is if AH, whatever representative you used, is the same as EH. That's the only way you're going to get the identity into your group. Now, Beth brought up an interesting point. What if you had, what if A is an element of H, and we consider the coset A inverse H? So the question is, will this be a subgroup? We know it's a coset, but will it be a subgroup? So that's a question that as we go on, we may want to think about. Potentially this is a subgroup, potentially this is a subgroup, we'll just have to see. All right. Although we won't get to it today, one of the big things that we're hoping to show eventually is why cosets are important. We'll start to talk about why cosets are really important at the end of class today and then on into Monday. Speaking of Monday, I just want to make sure that you're aware we do have a terminology quiz coming up on Monday. That terminology quiz will include some topics that we have not discussed. That's just the way that this class rolls. If I waited till we discussed every single thing, we wouldn't get it all in. So there's a couple of terms, Lagrange's theorem, which we'll talk about Monday in class, will potentially be on that quiz on Monday, even though we haven't discussed it. So make sure that you look over all of the things that are on the list. What I think I may do is give the quiz at the end of class rather than at the beginning. That way, if I talk about something during class that potentially ends up on the quiz, you've at least heard me say it. But you should study all of the terms in preparation for Monday. All right, so let's try an example together. This one, I believe, yeah, so this one we're gonna do together and then I'm gonna let you do one yourself. So what are all the distinct left cosets of K and G? So K is the subgroup of the dihedral group consisting of the do-nothing rotation and the vertical flip. So this is a subgroup of D4, and I want to find all the distinct left cosets. Okay. This is a little bit of a different question than the first one that y'all did, because I'm not looking for a particular representative coset. I'm looking for all of them. Okay. So remember the elements that D4 consists of. D4 consists of all of the rotations and it consists of all of the flips, across the diagonals or otherwise. So I have to look at what happens to this subgroup under left multiplication or composition, as is the operation here, for every element in D4 against this one. So we'll start real simply with this. I like to just start from the simplest ones and then work my way up. So for example, if I did R naught K, so I want to look at that coset, then I'm going to take everything that's in R naught and compose it on the left, or everything that's in K and compose it on the left with R naught. So what is R naught composed with R naught? Remember, compositions are right to left.
Still are not.
Still R naught. What is R naught composed with V?
Still V.
Still V. Do you suppose that there is another representative that also generates this coset? V. I claim that this is the same as VK. To see that, if I multiplied on the left by V, R naught, V R naught is just V, right? What is V times V? I'm going to say times instead of compose, but it's composition. So what is V times V?
Are not.
V times V is R naught, because if you do a vertical flip and then do a vertical flip again, it just takes it back to where it was. So you can see that V, the representative from V, is the same as the representative from R naught. They end up being the same coset. So I don't think there are any other representatives that'll work here. So what I'm going to do is I've exhausted R naught. I've exhausted R naught and I've exhausted V from the list. So the next possible representative is R1. So I'm just going to go down the list. R1 of K would be what? Well, R1 R naught is R1. What is R1V? Remember, you do V first, and then you do R1. This is helpful if you have the Cayley table for the dihedral group right next to you to look at. I think I have. I think I have a quick one that I could get to here. Yeah, it's kind of grainy, but it'll have to work. So if you look, here's the Cayley table. And we're doing R1V. So remember, that's V goes first. So it would be V and then R90 is R1. So V and R90 gives D, right? So V goes first. Is that okay with everybody? So actually, maybe I have that backwards because I have D prime written down in my notes. So let's look. I'm looking at R1V, which means V goes first. So R1V, yeah, so I had it backwards. So R1V would be R1 and V gives D prime, R1 and V. Let me just write it out so that we're comfortable with it. I'm not going to do this for every single one of them because it'll take a long time. But you've got 1, 2, 3, 4, 2, 1, 3, 4. That's if you do the vertical. And then 3, 2, 4, 1 if you do R1. That's the same as doing the off diagonal. So if you do a vertical flip, so flip across the vertical axis, you get this. If you rotate 90 degrees, you get this, but that's the same as going from here to here by doing the off diagonal flip. So flipping across 2, 4, which would switch 3 and 1's position. So this is the off diagonal. And I think what you can see is that's the same thing you would get if you used the off diagonal as a representative. All right, let me just fill in the rest of these and we can talk about them or any problems you may be having. So this will be R2 R naught, R2V. R2 R naught is going to clearly be R2. It turns out that R2V turns out to be H, which kind of makes sense, right? Because if you rotate 180 degrees and then do a vertical flip, it's like you're doing a horizontal flip. So this will be the same thing as H for the representative. And then finally, R3K would be R3 R naught, R3V, which would be the same thing as R3. And then this will be D, the diagonal. So it's the same thing as DK. So these are all of the 4 distinct left cosets. So there are only really 4. This is the first one, this is the second one, this is the third one, and this is the fourth one. They each have 2 different representatives, but they generate the same coset. Like the cosets are these right here. These are the cosets. So these are the 4 distinct left cosets of K in D4. Now, one of the things that I just want to point out, and we're going to keep track of this as we do more examples, if you take the size of D4 and divide by the size of the subgroup that we use to generate the cosets, the size of D4 is 8, K has size 2, you end up with 4. So notice that when you divide the order of the group by the order of the subgroup used to generate the coset, you actually get the number of, and we're going to keep tracking this, but you get the number of distinct cosets of that subgroup in that group. This tells you how many cosets that we should expect. Now, just a word of caution here, we get different cosets if I was to multiply on the right. So if I was to go through and redo this problem by multiplying on the right, we would generate 4 cosets, but they would be different from these. Because remember, D4 is not an abelian group. Doing it, multiplying on the right versus multiplying on the left, you're going to get different values here. All right, so I want to give you one to try. So you have the subgroup 03 of the group Z6. Which of these represents all the distinct left cosets? All right, you've got about 30 seconds. All right, the correct answer is B. The correct coset there are 0 plus H, 1 plus H, 2 plus H. Let's talk about it real quick. Z6, that is an additive group. So the coset notation for addition, you wouldn't be multiplying on the left by A, you would be adding A on the left. So when I start to think about the elements of Z6, Z6 consists of 0, 1, 2, 3, 4, and 5. Those are the remainders modulo 6. And I'm going to start at 0 plus H. So I'm going to take everything and add, so H is right here, 0, 3. I'm going to take 0 out of the group and add 0 to every element in the subgroup, adding on the left. So 0 plus 0 would be 0. 0 plus 3 would be 3. Do we agree that that is the same thing you get if you do 3 plus H? Because if you look at 3 plus H, 3 plus 0 is 3. 3 plus 3 is 6, but 6 mod 6 is 0. Similarly, if you look at 1 plus H, you would get 1 and 4, but that's the same thing as 4 plus H. If you did 2 plus H, add 2 to everything in the subgroup, you'd get 2 and 5, but that's the same thing as 5 plus H. So in terms of the cosets, there are 3 distinct left cosets. Of H in Z6. And that's not surprising because the order of Z6 divided by the order of H, Z6 has 6 elements, H has 2 elements. We expect there to be 3 cosets. Now we've done 2 examples where we found all of the cosets, and I want you to observe what's happening here. I'll go back real quick to the dihedral group example. If you look at the dihedral group example, what we've done is we've taken the entire group, which I have written out there at the top, and we've partitioned it. For instance, this subgroup are those 2 elements. This next subgroup, or this next coset, excuse me, represents these 2 elements. This coset represents those 2 elements. And then finally, this last coset is those 2 elements. What we've done is the act of creating a coset has created an equivalence relation on the original group, saying that R3 and D are equivalent to one another modulo this subgroup. And remember, I said last time that congruence classes and this concept of coset, this is an equivalence relation. And you remember from discrete that equivalence relations partition the sets on which they're defined. So since we have a group, we have an equivalence relation on the group that partitions the group into, in this case, 4 left cosets. And in this case, we have partitioned Z6 into 3 sets or 3 partitions. And notice that they don't overlap with one another. Once you have a coset, it doesn't overlap with any of the other distinct cosets here. All right, let's look at another example. Suppose that I was looking for all of the left cosets of the cyclic subgroup generated by 3 in U32. U32 is the set of all integers less than 32 and relatively prime to 32. So let me push a question to you real quick. The question I have for you is, if we are to do this problem together, how many cosets should we expect? So when we sit down together and figure out what they are here in just a second, how many of them should we expect to get? I know it's probably taking you a while to write out U32, so I'm going to give you a little bit longer on this. All right, you got about 30 seconds left. All right. Most of you have entered a response. The correct answer is A. We should expect there to be 2 distinct left cosets. Let's find them. So I'm going to start first with writing out what U32 is. U32 consists of everything less than 32 that's relatively prime. So basically throwing out anything that has a factor of 2. Turns out that there's 16 of those. If I look at the subgroup, the cyclic subgroup generated by 3, since this is a multiplicative group, I'm just going to continue to multiply 3 by itself. So you're going to get 3 times 3 is 9. 9 times 3 is 27. 27 times 3, I've got to come over to the side and do this. 27 times 3 is 81. And 81 mod 32 is 17. Then 17 times 3 would be 51. 51 mod 13 is 19. And then 19 times 3 is 57. 57 mod 32 is 25. Then you would get 25 times 3 is 75. 75 mod 32 is 11. And then finally, if you multiply 11 by 3, you get 33. And 33 mod 32 is 1. So we know we hit 1, so we know we're finished. So this is the cyclic subgroup generated by the element 3 in U32. You're just multiplying by 3 to get to the next one, but you have to reduce it mod 32 until you get a 1 to appear in the cycle, and then it repeats. Now, the reason that there are only 2 is the order of this cyclic subgroup is 8. You can tell that there are 8 elements. And so if things follow as planned, the number of left cosets is the order of the group. That's what we've been seeing, divided by the order of the subgroup. So the order of the group is 16 divided by 8. That's why we expect there to be 2. So this first candidate is to take the identity and multiply on the left the subgroup, in which case you generate, I'll write it in order here, 1, 3, 9, 11, 17, 19, 25, 27. So that generates the representative 1 times the subgroup 3 generates the subgroup. But if you look, all of these others are also representatives. So this is the same thing as me writing 3 on the left. So the coset with representative 9, the coset with representative 11, the coset with representative 17, 19. All of these give the same answer. So all of these generate the same coset, this coset here. And what you do is once you've exhausted all of the different elements that are in here acting as representatives, which generate the same set or the same coset, you look at the first element that isn't here that is in the group. So I've got 1, 3, but I'm missing 5. So the next distinct one is going to come from multiplying 5 on the left. So let's do that real quick. Multiply every one of these values in the original subgroup here, multiply by 5, and then reduce them mod 32. Does that make sense? So I know 5 times 1 is 5, 5 times 3 is 15, 5 times 9 is 145, which is going to reduce to 13. You're going to get 23, 21, 31, 29, and 7 in order there. So all I'm doing is taking the 5 and multiplying it by each one of these, and then reducing that result mod 32. And what you notice is the numbers that you get, there are no overlaps with this one. It's completely distinct from the original one. So this is the subgroup, which is, or the coset, which also has as its representatives 15, 13, 23, 21, 31, 29, and 7. All of these are equal. So there are indeed only 2 cosets, this one and this one, but notice it still partitions the set because all of these partitions the set into 2 pieces. So we still have the same behavior here. Is there anything about the examples we've done so far that people are having a tough time understanding? Okay, if there's no questions, let me go on to my last example. Let us find all of the distinct left cosets of the cyclic group generated by 3, but this time it's in an infinite group. It's the first time we've looked at an infinite group here. So I want to find all distinct left cosets of the cyclic subgroup generated by 3 in the infinite group of the integers. So I know the integers, I can think of this as being, you know, this set here. I know what Z looks like. The cyclic subgroup generated by 3 is this one. Remember, Z is an additive group. So I'm looking for all distinct left cosets. So what I'm going to do is I'm going to pick an element from Z. There are infinitely many of them, but I'm going to pick an element from Z and I'm going to add it, since this is an additive group. This is an additive group. I'm going to add my representative to every element in this subgroup. So I'm going to start with the most obvious one. Let's start with 0. If I add 0 to the left, well, I just get everything back, right? So my question to you is, what is a better way to write down this coset? Or a better way to think about it?
If you write it in mod 3,
Yeah, this is the set of everything that looks like 0 plus 3k, such that k comes from Z, right? Because that's literally what this says. Like if you look, you've got 0 plus this thing. Well, what is this thing? What is this subgroup generated by 3? It's the set of all the things that are of the form 3k such that k is in Z, right? Well, all we've done is add 0 to it. So we've added 0 to it, added 0 to it. It's still the same thing. That's all we've done. And this is going to be the same if I add 3 plus 3k, right? That's still the same. So 0 plus 3 is the same thing as 3 plus 3. Like those are the same thing. So there's one. What are the others? Well, I can look at the one that's generated by 1. So the representative 1. That would take everything in this set and add 1 to it. The way to write that is it's all the elements 1 plus 3k, such that k comes from Z. I can also look at 2 plus that set, which would be adding 1 to the one we just did, or 2 to the original one, which is the set of all elements 2 plus 3k, such that k is in Z. So I want you to look, because what we've done here is really quite spectacular. We've taken the integers, which is an infinite group, and we've basically said that in terms of their congruence modulo this subgroup, there's really only 3 distinct left cosets. You get things that are 0 mod 3, 1 mod 3, or 2 mod 3. So this suggests the following. It suggests that if you look at Z mod its cyclic subgroup generated by 3, that this is isomorphic to or in some way related to Z mod 3. Now, this is a notation that we're going to pursue much later in the course, but all I'm saying is if you take Z and you arrange all the elements in Z under a congruence based on this subgroup, really what you're doing is replicating Z mod 3, because either you're 0 or you're 1 or you're 2. And everything in Z behaves like either 0, 1, or 2 under this congruence that we've mapped onto it. So I'll explain more about this notation later in the course. But when we get to this notation later in the course, I kind of want you to think back to this example. This is our way of putting an equivalence class relationship onto this infinite group. basically partitioning it into 3 sets. All right. We got 3 minutes left. Here are some of the properties of cosets. A lot of these we've already discussed. We've discussed this one. We've discussed this one. We've seen this one. We've seen that since they form a partition, that either their cosets are equal to each other for a given representative or their intersection is empty. They don't overlap at all. I want to talk about number 5 real quick down here at the very bottom. Number 5 at the very bottom says that the order of a coset with A as a representative is always the same as a coset with B as a representative. And this doesn't matter what A and B are. What I mean by that is if you generate a coset for a given group and a given subgroup, all of the other cosets for that subgroup will have the exact same number of elements. If you go back and look at our examples from today, we've seen that, right? This coset had 8 elements. This coset had 8 elements. Each one of these cosets has 2 elements. Even though they have different representatives, they still have the same order. So the order of a coset is locked in the moment you tell me what subgroup you're working with. It doesn't depend on the representative. So the order of a coset does not depend on its representative. We talked about these definitions last time when we were doing the congruence class stuff about what it takes to be equivalent mod a subgroup. So remember that 2 cosets are the same, or your equivalent mod H. That's another way to think about this, is that your equivalent mod H if and only if A inverse B lives in H. That's the left coset notation. And here your equivalent mod H if and only if AB inverse is in H. So we talked about that equivalence relation last time, talking about how the difference of the elements has to be back in the subgroup, and that's our definition of congruence modulo subgroup. So these are the properties of cosets. I would refer to this page when you're doing some of the proofs involving manipulating things from cosets, because these are the properties you know you're allowed to use. One of the big ones that we set at the outset, the only way that this is a subgroup is if the representative belongs to the set already. Okay, so the only way a coset is a subgroup is if its representative is in the subgroup to begin with. All right, I think that's all I need to say for today. This gets us through cosets pretty well at this point. Hopefully we have a good understanding of what a coset is and the kind of structure that it imposes, the equivalence relation structure that it imposes on a group. What we'll do is we'll look at the consequences of all of this on Monday. Now that we have this coset structure, what are the consequences for us in terms of looking at group structures based on that? And that's something called Lagrange's theorem, really important theorem in the course. So see y'all back here on Monday. Hope y'all have a wonderful weekend. Remember to study for all of the terms for Monday's quiz. Have a good one.
Thanks.
Hey, Dr. Arkey.
Thanks, you too. Have a good one.